Okay, so let's start with our discussion where we have left yesterday. Hmm? So you see, yesterday we were discussing about the photolithography process. Okay, and we have completed that. And now, today, we'll see the other processes. Uh, this particular oxidation, then sort of diffusion. So related to the photolithographic process, whatever was required, the things like etching, the exposure to the UV, and then the etching, okay, and the other processes we have seen yesterday. Now today we'll concentrate on the other processes. So let's see how much we can complete today. So whatever we'll complete today, the remaining we will do in the next class. So even before photolithography, at sometimes you have to like oxidize the surface. So when you oxidize the surface, then there are various methods. I'll come to this particular thing. But when you oxidize the surface, then there are various methods. Like you can oxidize with the help of what is called as the chemical oxidation. So in chemical oxidation, what we do is we boil the this our wafer in the HNO3 solution. Okay, and then this HNO3, this reaction takes place, and we get what is the silicon dioxide and the byproducts. So the silicon dioxide, what we get is over the silicon. It is grown. I mean, it is like the layer of the oxide is formed over the uh, above the silicon surface. So this is one of the method. Then the another method is the anodic oxidation. Anodic oxidation is more or less similar to your electrolytic cell. So in that we use two electrodes. One is of silicon and one is of another metal. And then like the reaction takes place into the this you apply some voltage and the reaction takes place on the anode, and the silicon is like used as an anode. So the oxide grows on that surface on the silicon. But then these two methods are not that much used in VLSI. Okay, the reason being that they do not give that high quality silicon, this oxide layer. We want good quality silicon layer. And the other reason is that you will see, I mean, you'll understand that the reason is like why we use the other, this what is called as the thermal oxidation rather than the anodic oxidation or the chemical oxidation. This particular chemical oxidation and the anodic oxidation have the advantage that they can be carried out at the room temperature, whereas the thermal oxidation need very high temperature. Okay, but the good thing is that in thermal oxidation, the surface is of very high quality. The reason is in thermal oxidation, when you do the thermal oxidation, so you actually enclose the wafer in a closed chamber, and then you increase the temperature in the presence of the ambience in that chamber is oxygen. Okay, so in the presence of oxygen, when you increase the temperature, then thermal oxidation takes place. So it is not like the oxide layer will be grown, and will be just deposited. It is actually grown. So there is a difference between growing and deposition. So when you deposit something, then there are various methods of deposition. So we'll see them. But in deposition, actually you grow a layer of Si, or what, I mean, not Si, but whatever material you want to make, so that that layer will be grown over the surface. But in case of growth, what happens? The oxide actually penetrates into the silicon surface. And when it penetrates, some of the silicon present there itself forms the compound, and it becomes like SiO2, right? So some of the surface gets like, I mean, forms the SiO2, becomes the SiO2. So later on, when you etch it out, okay, with the use of whatever method you are using, so that particular surface will be removed. That surface, the top layer will be removed. So that top layer removal is actually good for the silicon for our electronic purpose. Why? Because when we started doing the things, most of the impurities or like whatever things were there, so the defects and all those things, okay, the dangling bonds and all those things were present on the surface. So when that surface is becomes the SiO2, so and it is removed, so you get a good quality surface which was earlier uh, below the surface, okay, which was below the surface. Now you expose it after the this etching out. So that is what the good thing is. So this is the one of the reason that you use thermal oxidation rather than the other oxidation methods. And this oxidation is basically of two types: wet oxidation and the dry oxidation. So when you do wet oxidation, so it is like in presence of water vapor, okay, or like when you increase so much temperature, so there will be water vapor on it. So it's a closed chamber. So it is done around 900 or 1000 degrees centigrades. And the if we see the mathematics of it, then we can see that the quality of the oxide is not that good, okay? Because the water vapor is present, so the quality is not that good. Poor quality oxide you grow, and this oxide is used for uh, your particularly it is used for inactive regions where the regions are where the MOSFET is not built. So particularly this is used for your masking, okay, masking the regions wherever you want the photolithography, wherever you don't want the photolithography, that window you don't want to expose. So that regions will actually, when you will do the processing, so this oxide layer will work as a mask. So it is used as a mask. And the other use of this oxide layer is it is used for isolation between the devices. So as a field oxide, FOX, which is generally known as FOX in VLSI terminology. So field oxide, it is the oxide is used this the oxide growth grown by this wet oxide method is used for isolation and for the mask purpose. And the growth rate of this oxide is also very high. So it have higher growth rate. So that means that whatever amount of thick layer you want to grow over the surface, then the time it will take will be less. So let's suppose you want to grow a 100 angstrom this na oxide layer, okay, 100 to 100 angstrom oxide growth layer. So then time will be less, because if it is if I mean this thick you want this thick oxide layer you want to grow, so if it is a slow process, then it is going to take a lot of time. So then the throughput reduces. So that is what the thing is. So you use wet oxide, because in the wet oxide the quality is doesn't matter that much, okay. The quality matters in the thin oxide, okay. The thin oxide should be very fine and should have a very high the breakdown voltage as well, okay. I mean it should have the it should able to help, I mean able to uh, I mean have the this thermal stress as well, thermal stress, okay. The thermal and the electrical stress, it should have the ability to withstand that stress. Okay, so the dry oxidation, the other method is the dry oxidation. So in thermal oxidation, we use wet oxidation, and the other one is the dry oxidation. So this dry oxidation is basically doesn't use water vapor, and you use the I mean the temperature is around 1200 degrees centigrades, and you don't use water vapor. You use the like sort of dry gases. Okay, so the dry gas of this dry oxygen, so that you use. So then this particular thing is done at a constant temperature, and whatever uh, I mean, it is just opposite the wet oxidation. So the growth rate of the dry oxidation, the oxide grown by the dry oxidation method, is like the growth rate is slow. Okay, so growth rate is poor, I should say. So the oxide which is grown by this method grows very slowly. So it takes time. So the throughput reduces. But then the quality of the oxide is very high. It's a very good quality oxide. Okay, it can withstand high temperatures and it can withstand higher voltages also. When I say high quality, so it means like the trapped charges will be less, and also the pinholes, the possibility of having the pinholes into that will be also less. but still it have some. Okay, so that we will consider later on when we will evaluate the quality of the this oxide. So this is what the dry oxidation, and it is used for the gate layer. Okay, so wherever you are going to form the gate of the device, so it is used for the gate oxide, as a gate oxide, not as the field oxide, but it is used as a gate oxide, as a thin oxide, right? So that is what the advantage, I mean, that is what the wet oxidation and the dry oxidation is. So once the oxide is formed, then there is like oxidation layer is formed. Then, as during the discussion in the first unit, we have seen that there are trapped charges and the other charges which gets trapped into the oxide layer, and this field oxide and this gate oxide, and then they create problem, or during the analysis, during finding the various threshold voltages, they interfere in between, and like uh, interfere with the threshold voltage. So the threshold voltage gets changed because of the oxide quality, and the amount of charges which are present there. So you see, this oxide, basically, you see what you are doing is you are using some materials to make these things. So the materials are not 100% pure. They have some impurities in them. So when you do this all processing, when you are putting it in the ambience of the oxygen and all these things, so they have certain type of other, like impurities, like if they have sodium and chlorine type of the sodium and potassium type of impurities, then they get also trapped into the this oxide layer, and they form the mobile ionic charges. Okay, so they looks like ionic charges. So they I mean, they very much interacts with your threshold voltage, and these mobile ionic charges uh, should be least present. If they are at all present, then you do certain methods, certain processing methods, so that this mobile ionic charges should not present. And the very simple method is this oxidation is done in presence of, like rather than using the pure oxide, you use oxide, I mean, with chlorine or with halogens, I should say. So chlorine or fluorine or bromine you use. So what happens when this chlorine and bromine gets into this during the formation of the oxide? So when they interacts with this, when they find sodium somewhere or the potassium, so they form the compounds like sodium chloride, NaCl, or the KCl, and then they becomes inactive then. Okay, so then like this mobile ionic charges can be very easily, this problem can be very easily solved by using the use of oxide or the halogens into the ambience. But then the problem of using halogens is that if the concentration becomes too high, then the sort of pitting can takes place. Okay, so that is what pitting of the surface. Pinholes can be created into the oxide layer also. Okay, and sort of small pits can also be created. So that is what the disadvantage of this. So you can use this, but the concentration of this, it should be in very less quantity. Other than that, there are always some trapped charges present into the in the oxide layer. So we get like concerned about more concerned. I mean, this fixed charges are okay. They are fixed, they remains fixed, so we don't worry much that much about them. But the interface trapped charges and the oxide trapped charges creates a lot of problem again, and there are methods to reduce them as well. Okay, so I don't remember those exact methods, so what are that? But then there are methods to remove them as well. Okay, so fixed charges and the oxide charges, you can remove them. I mean, you cannot completely remove them, but you can like somewhat play with them, and can reduce their presence, okay, with some of the methods. So your oxide quality is basically decided based on these things. So once your oxide is grown, so then you actually have to like characterize it. So when you characterize it, whenever I say characterization of certain thing, so actually you see that what is actually, I mean, you have targeted something, that the thickness should be, let's say, for gate oxide, the thickness should be, let's say, 10 angstroms. Okay. So then whether it is 10 angstrom or not, so you have to verify everything. Okay. Whether the quality, what is the amount of trap charges into it. So if you do this, then you call it characterization. So when you do the characterization, so again, there are like a few things which you do for the characterization. First of all, you see that what is the amount of like charges into it. Okay, and then you see also that what is the amount of what is the layer of thickness which you have made. Okay, so apart from that, I mean, for this also there are various methods, fringing method, and usually what is used is the capacitance voltage measurement method to find the thickness layer. Okay, so and this is also used for the measurement of charge present. So if the number of charges are more, then you're obviously the capacitance will get affected. Okay, so the capacitance voltage measurement method we use basically to characterize the oxide layer. One thing, and then you also use the, I mean, the breakdown voltage. You also have to find the breakdown voltage of the oxide layer, whether it is like within that range or not. Hmm? If it is like very poor, if the breakdown voltage is very low, so the device will not be able to withstand the stresses, the electrical stresses. And then there is like the pinhole, the checking for the pinhole, that how much pinholes are present. So when I say this characterization, so these things we have to do: the oxide thickness, the trap charges, amount of trap charges, and then the this particular breakdown voltage, and your pinholes presence. So pinholes presence is like done by the help of this microscopic view. So if you just see the surface in the under the microscope, you just put it under the microscope, the sample under the microscope, then you can see that how much amount of pinholes are present there. Okay, and if you like want very precise, then you can go for this scanning electron microscopy or sort of something like that. So this was all about the oxidation. And let me tell you, when you say, I mean, this particular slide we have missed. So I just wanted to give some more time to this particular thing.
Hello, sir.
Yes, please.
So your slide is not changing. I think it is on first slide.
It's first slide. Which first slide?
Silicon
Yes, sir.
wafer.
First slide only, sir.
Which is the, I mean, what you can see, you just read it out. Oxidation, can't you see?
Silicon wafer
Sir, silicon
oxidation.
wafer.
Yes, sir. Oxidation is the process by which a layer of
So,
silicon
so
dioxide is
silicon
grown.
wafer, and then there is a disc, and then the oxidation method is there.
Yes, sir. Yes,
Okay,
sir.
so this is
Yes,
what
sir.
you can
Only
see.
that, sir.
You cannot see the oxidation
Yes.
details which I have shown you.
No,
Are,
sir.
so you must have told me earlier. I have completed this whole discussion. Chalo, anyways. So let me show you. Still, is it changing now?
Yes, sir. Now it's
Okay, so
changing.
actually I was discussing this particular slide, right? So oxidation, so methods
Yes,
of
sir.
oxidation I have told you: chemical oxidation, anodic oxidation, thermal oxidation. Okay. And in this thermal oxidation, again, I have told you this wet oxidation, dry oxidation, then the quality, this growth rate, poor quality. So this is what I was like discussing. So this is what the things were done here. And then the oxide quality. So the interface trap charges, fixed charges, oxide trap charges, and the mobile ionic charges. So this was I was discussing. Okay. So in one
Yes, sir.
slide, I have like written all these things to discuss them in like in short. Acha. Apart from that, so I'll keep the presentation in this mode only, because if the slides are not changing, then it's an issue. Okay. So you see, is it like properly visible now?
Yes, sir. But first slide is there. Only first.
No, which one? Still, it is not changing.
Uh,
Again, it is.
so I think it changed to that silicon wafer, that
No,
disk one.
no. I like brought it to that this slide.
Okay,
Okay.
okay.
So now you see it is
Yes.
changing again.
Yes,
Okay,
sir.
okay. So I
Now,
brought again it to that particular slide. So now you see, I just wanted to concentrate on this particular figure again. That as I have told you, that the silicon dioxide is not just form. You just don't deposit the silicon dioxide layer over the silicon substrate. What you do is you grow. So the basically, as I also said, that some of the silicon is like eaten up. Okay. So the thing is like how much silicon is eaten up. Okay, how much percentage? Let's suppose you have like some silicon wafer. So in this diagram you can see that this dashed line is the surface which you started with. Okay, so at the beginning of the process, this was the surface, the dashed line. Now when you do this oxidation, the thermal oxidation, so what happens is this particular this dark gray region, this gray region which you can see here, light gray region. So this is where you get the oxide, the silicon dioxide grown up. Okay, the TOX. Now in this, like how much is the surface which is eaten up basically. So whatever is the thickness which you have grown, so out of that approximately 44%, okay, approximately 44% is like this region which is into the surface, which is into the which gets I mean this oxide gets penetrated into this. So this region is formed as the silicon dioxide, and the 55% is the pure region. Okay, it is also the silicon dioxide, okay, the same quality, but the thing is this 55% is grown above the surface, and 45% approximately is like formed from the substrate itself. Okay, and how you can do this, how you can find this, it's a very simple, it's not difficult to find. You just write the equation of like the reaction which is taking place. So it is the earlier it was silicon is present, and then you write oxygen, so Si plus O2, and then the product is SiO2, let's say. So you just write the weights of that equation, okay, like the atomic weights of this compounds. And once you write the atomic weights of the compound, and if you know that what is the region, so because you know that how much area is this, if you can like characterize it, find the thickness of this layer, okay, then you can see that what is the amount of volume is there. And if you find the volume and multiply it with the density of the material, okay, you know very this silicon dioxide density, and so we know this silicon dioxide density. So when we this multiply with this volume with the density, we find that what is the actual weight present there. Okay, and by this particular calculation you can easily find that how much oxide is like the silicon is eaten up to form the silicon dioxide. Okay, so it's not difficult calculation, because actually if you I mean I just didn't got the time to enter that, to write that particular thing in the slide. Otherwise I could have shown you that. Okay, but you can do it very easily. You just try it out. If you're not able to do it, then just tell me. I'll show it to you in some tutorial class or something like that. Okay, or in some class when we will take it. So after that oxidation, let's move on to the another process. So there's another process is your diffusion. So diffusion also have like many parameters, and this diffusion basically is for like growth. I mean, not growth, I should say. It is to make the regions. Once the oxide region is formed, the gate oxide and the thin and the thick oxide you have made. Now you want the source and the drain regions as well, the formation of the source and the drain region. So diffusion is one of the method to make the source and the drain regions. So first of all, what you have to do is wherever you want to form the source and the drain region, or any other like well region, N well region or the P well region, that you open by the help of photolithography. So that window particularly is opened by the help of photolithography, and once that window is opened, then you expose this material to that particular whatever diffusant you want. Okay, so whatever type of impurity you want to dope with in that particular region, you just expose that to it. Okay, so then because of the concentration difference, the material gets penetrated into the surface, and this particular thing is done at around like 1000 degrees centigrades. Okay, and the penetration quality depends upon the concentration of the doping, the dopant which you are using, and it also depends upon the temperature which you are using. Okay, apart from that, it also depends upon the size of the dopant. So let's say suppose the silicon size, the atomic the size of atom is, let's say, something. Okay, and if you are like doping it with a material which have very high atomic size compared to the silicon, then what will happen? Once it get inserted into that diffusion, then it will create a lot of stress into the crystal. Okay, the crystal is like the in the crystal the silicons are sitting, hmm, and they have some interstitial sites as well. So if the dopant size, if the dopant size, the atomic size of the dopant is not comparable to the size of the silicon, then also it creates a lot of stress into that region. Okay, so that is what the diffusion matters. So the dopant concentration, the size of the atom, okay, and when you say that what type of stress it creates. So there are like various types of stresses which it creates into the this material, but that is not our purpose to study. Just I'm telling you the things in the short, that the diffusion is used for to form the N and the P regions. Okay, source and the drain regions. And the thing is, when you try to diffuse the things, you want like it to be very fine, but very fine in that region only. Okay, the source region should be very strictly defined, but actually by diffusion, the quality of the N region and the P region which you make by this diffusion process is not that good, because it is not like the diffusion will take place in the vertical direction only. It The diffusion also can happen in the, I mean, it usually happens in the lateral direction also, in the horizontal direction also. So then your diffusion, if takes place in the lateral direction, so some of the region, so the diffusion region goes under the gate also. So that is what the reason is, that when we were showing the diagrams in the very first unit, I have shown you that the source and the drain regions were under the gate region. Okay, so some of the gate is over the source and the drain region. So there was some overlapping, and because of that, what happens? Some of this capacitance comes into picture. So the oxide related capacitance which we have studied earlier is because of that only. Okay, so this diffusion is not very like perfect. So to like make it and this requires the high temperature also. So the other method to do this is ion implantation. So what we do is, rather than using the diffusion method, so you see diffusion is used, it depends upon the application for which you are making the device. Why? Because the diffusion method is like not that much costly. Okay, it will be like less costly. But if you want very precise source and drain region for an if like suppose you are using very like the feature size is very small, or if you are using certain this particular device for a very strict application, let's say for satellite applications, then or I mean rocket applications, let's say. So in this case particularly, you want very precise things to be controlled. So then in that case, you use ion implantation. This is very costly, but still it can be done. Okay, very precisely. The source and drain regions. Okay, the implantation of the source and the drain regions. And with this, you can have like this process can be done at very low temperature. Basically, it is done at the room temperature. So this is the only process which is done at the room temperature in case of silicon wafer processing. And the thing is, like when you do ion implantation, so ion implantation is nothing. You again put the wafer in an ambience, and then rather than putting the dopant in the form of chemical and allow it to diffuse into the surface, you put the electron gun. Okay, so sort of you use an electron gun, a high beam gun. So then with that high beam, this concentrated beam, so you can like easily do the implantation in a particularly specified region itself. Okay, so then there will be less possibility of diffusion and all those things. It's not like it won't diffuse at all. It will diffuse, because later on you have to anneal the surface. So when I say annealing, so let's see, like one by one we will move. So ion implantation, when you do, so what happens? You are forcefully targeting the this particular beam of that material into that surface, into that particular region. So what will happen? That particular thing will go inside that surface. Okay, it will penetrate into the surface. But then how much it will penetrate will depend upon what is the energy with which you are penetrating, with the electron beam energy. Okay, so if it have more energy, then the penetration will be more. If the beam energy is less, then the penetration will be less. So it depends upon the beam energy. Okay, one thing. Then uh, there are like, if you again, as I have told you that the same thing what it was like there, so again it will create like stress. If the dopant size is large, then it will create stress into the surface, or wherever this doping will be done. So it will create mechanical stress and the electrical stress. And the other thing is, because you are forcing the things with very high energy, so the surface gets damaged because of this. Okay, so to heal this surface, and when I say the surface is damaged, it actually loses its good qualities, the crystal structure it loses. So if the crystal structure is lost, then the electrical parameters, like the mobility of the charge carriers in that region, okay, the what I should say, resistivity of that region, okay, the conductivity of that region, basically conductivity or the resistivity, whatever you say. So that also gets affected. Then the presence of, I mean, some charges, some charge carriers are present. So the lifetime of the charge carriers also get affected. Lifetimes means how long that they will remain onto the, I mean, how much time they will take to recombine. Okay, so generation and recombination. So the generation and recombination also takes place very quickly if at all the charges are generated. So then you don't want this. Okay. So you have to heal the surface again. So to heal, what you do, you anneal the surface. So annealing is nothing but you again, because this ion implantation was done at room temperature, and you have deposited some of the things already, and those things cannot withstand high temperature. So you want certain process in which you basically heal the, I mean, you increase the temperature up to like less temperature compared to what you have done earlier. So it is in the vicinity of 600 700 degrees centigrades. You again increase the temperature. So when you increase the temperature, what happens, the surface gets repaired back. Okay, the crystal structure, because you are again imparting the energy. Okay, I mean, you are making, let's say somewhat it will get molten. Okay, so the crystal structure gets loosen up, and the crystal try to get reorient again. Okay, and whatever impurities which were, if the silicon was forced into the interstitial sites, the gap between the crystal structure, so then it comes back to the in that crystal lattice again, the position which it has lost. So it comes back to that position. So this is what happens by the annealing. So ion implantation, you do it for very precise this doping, to get very precise doping profile in the source and the drain region, but it has its own like disadvantages. So physically it damages the surface. Okay, and this ion implantation, this process is actually have some like the beam of ion, as I've said, the mechanisms used there is the beam of ion is used there, and then there is a sort of accelerator, so which imparts the velocity to it. Okay, and then there is a mass separator. Okay, so this mass separator is actually what, because this ion beam will have too many like impurities as well. So some heavy metals are there, or some iron compounds are there, iron is present, is also there. So then what you do, you use a mass separator. So separator is nothing but a slit is there. uh, in that slit only that particular ion beam is passed, and that particular material is passed, which you target. Okay, which is like targeted. Otherwise, if you don't use that mass separator, then all the compounds will get penetrated into. Just wait a minute. ना, सुनाई नहीं देते तो आप फ्लो रुक जाएगी ना। बार बार बजाने से तो मेरा मतलब काम भी नहीं कर पाऊंगा। Okay, so is this clear? Okay, fine.
Yes, sir.
Okay. So this was the acha. So the silicon dioxide, what we do is like deposit. So it's not only used to do the silicon dioxide, but we also use sometimes like the silicon nitride as well. Okay, so we will see like where we use the silicon nitride, where we use the silicon dioxide. So in one of the process which is called the low cost, we will use silicon nitride as well. So what is the process? We will see that later. That is not related now. So diffusion and implantation, we have covered things in short. Now, this deposition actually, if I'll start with this, so deposition is only remaining. So let's try to complete it, because rest of the things I have shown you, and the things is like the deposition. Otherwise, I'll do this thing tomorrow. Okay, in the next class probably deposition, and then we'll move on to the another things, because I have class at like again at 9, and I have to I mean take it physically. So I have to go into the department. Huh? So let's stop it here. Right? Okay.
Okay, sir.
Okay.